I have to really apologize this problem, but I know I have 10 minutes, so I'll fast up, I'll speed up then. I'd like to share some cases for how simple structures can be applied for automobiles. Well, this is a very well-known the diagram. So there are so many sensors, these days, and there are a lot of electronic, gadgets in the car for a the safety protection, environment protection, and the information and entertainment, so-called infotainment. And currently, there is over $15 billion of sales in the globally, and it'll increase quite fast, in the next 5 years. And in vehicle management, there is a lot of the sales in those areas, and we need many sensors like airbag or tire pressure monitoring system or exhaust protection to improve the safety of vehicle environment. So here's one example in the diesel particulate filter, so-called DPF. So if there is an exhaust line from the engine to the outside, and there is a filter for removing diesel particulate matters or soot from the exhaust gas of a diesel engine. But if it's gone, then you can see a lot of smoke here or some broken pieces here. So there is a need for the so-called particulate matter sensor or PM sensor, the detecting how this filter is doing. So it's quite simple and quite a cost-effective approach. This is quite necessary because the regulations, for cars in the following years are very strict. It's becoming strict, such that well, we have a lot of the gases, toxic gases from the car and the particulate matters, in the sense that in the Euro 6 regulation, in 2 years, we should have a 6.5 milligram per kilometers, less than that. And so that's quite strict, regulation. So as I said, in the Euro 6 regulation, it's got to be smaller than this. And another one is Tpms, which is quite well known and well, established, and for pressure, measuring tire pressures. But there is some unwanted effect, like a centrifugal effect on the pressure measurement. So we need the accelerometer to measure this, force to calibrate the pressure. And we may, add a energy harvester as a secondary energy source. So we'll take a look at 403. Here's how these are done, like acoustic waves. Like this is a resonator, and the frequency changes. With the quantity of PM. And another one is like a Bosch style. This is a resistive thing, such that there are two, the electrodes, and if there are, a certain amount of this soot or PMs, then it will conduct, so decreasing the resistance. And the third one approach is measure the differential pressures at the input and output. Input port and output port, and the measuring the pressure difference, how it's done. And another approach is called electrostatic induction, in the sense that when there is some called a sensor or sensing node, and then when the PM is the flowing, then the charges here, from the center. The charge changes as the charged particle moves. So here's some comparison, and so I guess because of time I just skip it. So our approach is quite simple, in the sense that this is a ceramic plate for good packaging, and then there is a one silicon structure here, and we put the signal line both sides, and on the top, and the heater line on the at the bottom, and on the top this is a signal line, and then this is a sensor area, and the heater in the back, in the back. So it's quite simple structure, and the fabrication uses only one single mask, such that we pattern this silicon structure up to about 40 microns, and then put some dielectrics on top of it, and then metal lines at the bottom. So it's only one single mask, simple process. And here is this slide shows those the lines, grooves on the grooves here for the sensor. And this is a manufactured and the packaged device, in the sense that this is the top portion and the bottom portion again, and then this is wired and assembled in this there. So this is a sensor tip, such that and it's plugged into the exhaust pipe. And the signal is the process using a charge amplifier, which converts the charge to the voltage, and then quite simple, again, the process, like a 5 kilohertz sampling rate for the data acquisition, and then we use a bandpass filter, up to 200 hertz. Usually we use, the signal starts at around 50 hertz. So, and then for there is a power supply noise at the 60 hertz, and it's harmonics. And then we measure calculate these the RMS values out of those. So this is the schematic of the readout circuits with the from 7 hertz to 10 kilohertz bandwidth, and most of the signals locates here, less than 200 hertz. So it's quite the simple circuits and structures. And here's the output of the sensor, in the sense that this is a PM in terms of milligram per kilometers, and then RMS voltage. So we have a kind of a linearity here, okay, and the sensitivity is 10 millivolt per milligram per kilometers. Actually, this is a kind of binary sensor, but for the characterization, we measure all these signals, and then at the motoring state without the particulate matters, the offset is about 1.6 millivolt. And then in this area, we check these things like the offsets, okay, and then this. So we think the lowest PM level is about 0.25 milligram per kilometers. If we convert it using the FFT, then we can see, some. It's not easy to see, but we can see some, the signals on several frequencies. So in the motoring state, we don't see anything here. And then if we increase the PM level, then the signal also increases, okay, as you can see here. And we have these are actually this 12.5 hertz signal is related to the engine RPM. So if RPM changes, then this frequency changes. So we have a kind of a clean signal out of this one, and then for the repeatability test, we measure the one time, and then eliminate the PMs by using the heater. So it's heated at the 650 degrees C for 10 minutes, and then redo it again. So it's quite close, for both of these, and so out of the first and second one. So at the 6.5 milligram per kilometer level, we could be able to get the quite consistent output out of this one. And this is supported by Hyundai Motors, so they are gonna, I guess, they are getting a Bosch, type sensors these days, but they're gonna, I guess, replace it in 2-3 years now. This is the silicon sensor area with this, the deep trench silicon pillars, and the left one is with all those PMs or suits. Okay, so you can see those floaty things here at the bottom and the side, and after heating, it's all gone, so it's quite clean. So it took only 10 seconds. Yes, for this heater, okay, at the 12 volt. And this PMs was exposed at 40 minutes, to the outside environment. And the second thing is accelerometer for the Tpms. I guess the Tpms and why it's useful. So I'll just skip it. Usually a TPMS has a pressure monitoring cell and the temperature and the acceleration, for the calibration. So they are called the P, T, and G cells, and then some signal processings, and then MCUs and the RF transmitters, because they are usually embedded in the real area. And there is a receiver here again. And so again, this is to compensate the effect of a centrifugal force, which generates the deformation of the membrane, measuring the pressure while the tire rotates. So, for a free scale, they use distortion bars, making the capacitance difference, or x-axis one. And for our case, it's quite simple. We have a mass and the piezoresistive, the piezoresistors on each corner. So when this, with this, for example, for the z-axis detection, these, the outputs and the resistance has some the patterns, associated with the input. And we use a bridging, circuit. So it's a silicon structure on the bore 3-3 glass, and then it's bore implanted for the bridge, and the size is 3 millimeter each side, and the mass is about 1 millimeter. So we had about 200 microvolt per G of the sensitivity, and that is quite, the linear output as expected. And the third one is energy harvester for this one. The tire rotates, in many different shapes. Okay, so if you use a 2D vibration energy harvester, then we could, get some energy out of it. So that it's a 2D, so that we have an anchor and then fixed electrodes, here. So it's basically electrostatic, so a capacitor change, it goes to the energy in the capacitor. It uses only 3 masks for the silicon etching and the oxide tail etching and the glass patterning. So this is the fabricated sensor, the harvester here. And out of the 1.2 the meter per sec scale of acceleration, then we have about 200 hertz of the resonance frequency, and so 45-degree input generates the maximum outputs, such that at the 1.2 we have about 0.7 microwatt, and this is a temperature change, so it's quite stable for the temperature. Again, I'm very sorry, for all the problems, but I think the automotive sensor, market will grow by, with the for the safety and the environment monitoring. And the automotive sensors, with the addition or combination of the some communication skill, the setup will increase the usage. Thank you very much.